Hi there, this is Emerson Sheldon for Lab 4 Oscillations. So for the introduction, the purpose of this lab is to observe and analyze a given spring mass system and tracker and plot the x and y position with respect to time graphs and compare these graphs to one generated from a computational model using GlowScript. We will also plot the change in energies from the computational model. And in the overview of the results, the net energy or the total change in energy is equal to 0, and then the observed position from tracker and positions in the computational model are very similar to each other. For the fundamental principles, we're using Newton's second law, the position update formula, the velocity update formula, the kinetic energy formula, and gravitational potential energy. And then the net force is going to be the combination of the spring force and the gravitational force acting on the system. And then also, for this, we'll be using the spring potential energy and the energy principle. And so the energy principle definition is the change in energy in a system is a sum of work done by the surroundings and the thermal energy exchanged with the surroundings. Energy can neither be created nor destroyed, it will only transform from one form to another. And so because of this, the total energy will be equal to the change in kinetic, the change in spring, and the change in, the change in kinetic energy, the change in potential spring, and potential gravitational, all equal to 0. And so the initial conditions, the system is the spring, the block, and Earth, meaning that surroundings are nothing, which makes work 0. The mass of the block is 0.402 kilograms. The spring constant is about 6.88 newtons per meter. The relaxed length of the spring is 0.127 meters. The block's initial position is shown, and then the block's initial velocity is all 0. And so then here's the experimental setup. As you can see, it is dropped. And there's about 100 data points, and it's the top graph. On the right is the position and time, the x position and time graph, while the bottom graph is the y position and time graph. And then you can also see, so here's the, data and results. As you can see, the first graph, this is just a closer up of the ones from before, but as you can see, the first graph is time versus x position, and the second graph is time versus y. And then moving into the GlowScript code, we first define the initial conditions. We define mass of the ball, and then the velocity and position of the ball. And then we also start time and the time loop, and then we use our regular constants, so our spring constant and our spring length that we already found, and then our gravitational constant, just of 9.8. And then we have we use this to find the L, like the length, using the ball minus spring position, and then L hat, so the magnitude of L, and then our S. So with this, we also calculate the gravitational force on the ball and just all the forces. So on the middle part, so we're getting our net force because we need to calculate our spring force and our gravitational force. And then we also do the momentum principle, Newton's second law, to update the velocity and the position. And then we also update the spring through our loop, and then we'll calculate the energy by using the code showed farthest on the right. And so this eventually will help with the velocity update and position update. We'll update the ball's position for every loop, and then eventually update L hat moving down the loop, so we create our energies and change in energies. So here are the results from the model. As you can see, we had change in energy graphs. We also have the comparative graphs for both model and experiment. In the first graph, you can see it's x position versus time, and the second graph, you can see y versus time. This is very similar to the results on, well, you can kind of see them, they're both in red and blue to see the experimental versus the model. And then for discussion and possible errors, as we can see from the last slide, the position from the tracker and GlowScript models are very similar except for a few areas. The possible sources of error for this might happen to be we did not include everything in the system. We did not consider drag force in the GlowScript model. Drag force did affect the block in reality. There is always possibility of error within tracker, like calibration error, tracking inaccuracies, and possible human error. And in the system in reality, by not completely isolating, there might be some work done by surroundings which we did not consider. And then for questions, for your model, is the energies principle satisfied? Yes, the energy principle is satisfied for the model because E is equal to 0, the orange line. Through the energy time graph, all the energies, kinetic, spring, potential, just all of them cancel out, giving us 0. The energy principle states that total energy over a given time can't be changed and should stay the same as shown here. And then for question 2, the period of oscillation, average estimation of period of oscillations for the x position is 1.614 seconds, and the average estimation for the y is 1.519 seconds. Even though the periods are very close, there's about a difference of about 0.096 seconds. This could be due to drag and couple nature of the spring's 2D motion. Okay, that's all. So thank you for watching.